Okay, now all that's done. We all know you're here for the big show. Give FX a huge round of applause for the schooling on disassemblies he's going to give you right now. Give him a round of applause.
Thank you. Welcome to a tutorial session. I am a little bit surprised at how many people actually want to build custom disassemblers. But that's a good development. What I'm going to cover is not just building a disassembler, but building a disassembler for an instruction set where you don't have a documentation. With most instruction sets, you do get a documentation, and why are my slides cut off? That is suboptimal. Anyway, so you're missing the bullet points. So we're going to quickly talk about the motivation behind this talk, a introduction to the field. It is not a regular CPU that you're dealing with on a daily basis, so we have to cover a little bit of groundwork. And then I'm going to talk about how we find the bytecode, how we recognize it, how we see basic properties of the bytecode, how we implement an IDA CPU module to put the disassembler into IDA. Oh, great, thanks for fixing it. And some more advanced topics that you're going to face if you want to write like a complete disassembler, and then we end up reading some code that we're not supposed to read. So the general motivation is like this. This is what you get, and IDA tells you, I don't know what to make of it. The story behind this is a little bit embarrassing because it taught me that I'm no longer a teenage hacker. I got a call from a friend who worked on the Stuxnet case, and he asked me whether I know any old fart, that was his saying, that still learned PLCs, which happened to match to myself. So I ended up dealing with this part of it. So more specifically, in June 14 this year, Frank Baldwin, an independent researcher who's not working for antivirus companies, actually figured out that the antivirus companies were so busy jerking off about the fact that there was an LNK 0-day in Stuxnet that they completely missed the fact that it had payload that actually did something interesting. A lot of people started speculating about Stuxnet, and still do. Very few people actually read the code. Here's a general recommendation. Read the fucking code or shut the fuck up. And so in the Stuxnet code, there were a couple of blobs that were apparently PLC code. And those needed to be analyzed, and the information that you could get off the internet wasn't really reliable and wasn't actually coming in the speed that was required to figure out what Stuxnet actually does. So, intro, now we need to look at PLCs, right? The stuff that I learned PLCs on in professional school is actually like this little thing to the right. It's a very simple programmable input-output controller, essentially. It's designed for electrical engineers, not for programmers, and it's actually just designed to virtualize, as we would say today, and abstract a fixed wiring configuration of an automatism. The default access, you have digital inputs and outputs that you can program, and there's some analog digital converters connected to them, and then you can, drive motors or pumps or dildos or whatever. You can actually do that. So it's from a programming perspective, it's a one register machine. It actually has usually only one register and accumulator. Newer ones have more than one accumulator register, but you can't address them directly. Modern PLCs, as I had to learn the hard way, are a lot more complex. So how do you program those? This is fairly interesting. The programming of PLCs So the PLCs are all vendor specific. However, the programming is actually standardized by the IEC in the 61131 standard. They also standardized other interesting stuff like VHS video and 19-inch racks. And what they define as a set of programming languages. The first one is the most commonly known ladder diagram. That's what you see up here. It actually looks like an electrical engineering wire-up painting. Then there's the function block diagram. This is from Wikipedia. This is actually part of the Genesis project, Gemini project. From NASA. They somehow gave it to Wikipedia for whatever reason. To the English one, of course. The Germans deleted it. Then you have a structured text representation that you can write in that pretty much looks like Pascal with all its beauty. Then you have the instruction list, which is the closest you can get to the feeling of an assembly. And then you have a sequential function chart. You can already see that it's fairly complicated just to, use a sequential function chart just to open and close a door. Manually, that is. The IEC also defines a standard set of libraries. Think of it like your libc. There's just a standard set of instructions, functions. So the PLCs actually don't natively execute the code that you're pushing on them. Most of the older ones that are still in use actually emulate the code, so there's an actual operating system layer, thin layer on top of the real hardware. The real modern ones now use ASICs that can natively execute this bytecode. And what you need to keep in mind with PLCs is that they execute in so-called scans. So you don't have a continuous execution as you would expect it from a regular CPU, but you have like a hamster wheel cycle that goes, it reads all the inputs, converts them, you have an analog input. If you digitize it, you need to set a defined point in time when you take the measurement. And this is what is done first. Then the main code is executed with all the other code that might be called from the main block. And then the outputs are set according to what the code did, right? Relatively simple. Now, if you're dealing with PLCs, you always have something like a programming device. And here, to the left, you see the easiest and smallest version of a programming device. And this is all you need to actually program a PLC. Nobody does that anymore. People use Windows applications and fancy GUIs and stuff. But this is actually like the most minimum programming device that you can have. If you obtain one of those, you should not go to like the automatic casinos that we have in Germany, with the coin automats, because those people get really nervous. They totally don't like you having that device with you. So when you look at the PLC structure, to the right we have the inputs and outputs that are somehow connected to the whole thing. And then what you see in on top at the system memory part, it's called the process image input table and output table. Those are the tables that actually get the digital measurements or set the digital outputs. And those are fairly important for the PLC because this is what the PLC thinks it sees on its sensors. Then you have a bunch of system blocks, code data blocks, and then to the left you see the programming device where you have the user program, a symbol table, and the hardware configuration. So, enter the Siemens specifics. Simatic S7 and the Step 7 programming environment. Simatic is a word combination from Siemens and Automatic. Under this brand, they built PLCs since '73. Now you're probably seeing why I was asked about the old fart. They're actually doing it longer than I exist. For the step 7 or S7, which is current now, the bytecode is called MC7, and the development environment is called step 7 for Steuerung einfach programmieren. Isn't that beautiful? In English, controllers easily programmed or fucked up. They do support a couple of the IEC languages. They have the ladder logic and the function plan and all that. And here you see German abbreviations in here. That's because this is built for electrical engineers, and Siemens being a German company, they actually internationalized the programming language. So be really careful if you look at step 7 code, it might be German. Because a German electrical engineer cannot be bothered to understand that AND is A, so they actually have a German instruction set version that has UN for an AND operation. This is why you actually need to know like both abbreviations, because all of them are translated. They have 4 other optional programming environments. Full PLC simulation package, including a hardware design package where you can drag and drop like your PLC stuff so you can simulate it, and a couple of tools to talk to the PLCs and debug them and stuff like that. The software can be obtained with a 14-day free trial, so for the purpose of writing our disassembler, we don't actually need to pay for it. Of course, there's other ways to get the software. And as Miko pointed out, it's fairly obvious that Iran runs the software too. And apparently whatever their purpose was, it wasn't 14 days. So okay, so this is how it looks like when you program in this. And this is, as you see, the English version. And the actual code is the little block in the middle that has A and equals and stuff. And then what you do when you're starting to look for the bytecode, you should not try to export, like compile code and export it into a file format, because then you're facing 2 problems. You're trying to understand the file format, and you're trying to understand the bytecode. So what's a lot better is to get a simulation environment, which is shipped with this toolset. So this is how the simulator looks like, pretty trivial. And then you take regular Windows tools, like the Process Explorer, and go and explore where this tool is actually writing to. In this case, it is writing into a temp file. And it's writing to that all the time when you say compile and load it into the simulation environment. So then you simply start a clean PLC and write some code in that, and then compare the 2. Actually, I wrote this tool for barcode analysis, and it turns out to be quite useful for that type of work as well. So what you see to the left is this temp file that the emulator works on. And in the clean form, and what you see to the right is the same file, but the darker pixels are bytes that have a value different from 0. The darker the byte, the more F's in there. Once you have this initial foothold and you know where you can get the bytecode from, you should actually familiarize yourself with this environment. That's easily the most painful part in the whole exercise, because you actually have to learn to use it the way the original vendor wanted you to use it. It's helpful to have basic introduction material. You should actually go through the basic introduction material and learn what the programming and debugging cycle in this environment is, because you will do it a lot, and it will definitely help you to be familiar with the basic steps and not fail at the basic steps all the time when you're hunting for like 1 bit that you're lacking at some point. What's very helpful, because vendor documentation tends to suck, what's very helpful is looking at university websites and looking for transcripts from students that had to learn this bullshit for some reason and never used it again. So here's an overview of the STL, of the assembly-like language in step 7. So what you see here, like for example, the bit logic instruction, the equal sign is a instruction. So the same holds true for larger than and smaller than. That actually got a couple of tools that I was using this code with because they used as an internal data representation, they used XML. And they didn't expect that instructions actually have a greater than sign themselves, so that kind of broke them. So in general what you have is the bit logic instructions are the most important on a PLC because they work on the inputs and outputs. You have comparison instructions, of course, so you can do conditional code flow. You can convert, you have counters. Counters are natively in PLCs, they're a very important concept. The same holds true for timers. Then you have data blocks. The PLC is from the MC7 bytecode level. It is not a von Neumann architecture. It actually feels more, from the programming point of view, it feels more like a Harvard architecture. So you cannot mix code and data easily. So what you actually do is you have different types of data blocks. And of course, instructions to deal with them. Logic control, conditional jumping, integer math, floating point, loading and transfer, which is needed a lot because you only have one fucking register. Shift, timer, word logic, and the accumulator instructions. So there's quite a lot to cover. So how do you start recognizing your code? You start with the most basic functionality that you can find. So you're looking for something very simple. In the PLC case, it was loading a small value into the accumulator register. And then you do that multiple times. That's the easiest way to actually recognize the pattern in hex when you look at the hex dump, right? If you can, use hexadecimal notation right away, because if you type hex, then it's easier to recognize it, or recognize if it's missing. So here we do have a case where I just loaded 7F frequently into the code. I'm too short, then. And so you already see a pattern where 7F shows up on a regular basis, all 4 bytes. What's fairly important is to start with small numbers. Like, do not load 31337 as your initial value. It might look lead, but it's actually a dump move. Because instruction encodings tend to be different for large and small numbers. This is step 2. You're increasing the size now of the immediates that you're loading and see whether the instruction actually changes, whether you're dealing with multiple instructions that do the same thing, but depending on the size of the operand are different, or whether it's the same instruction set. This being Siemens, of course, the first is the case. The second thing that you then can do is you take those loading instructions that you now automatically recognize with your pattern matching brain. So you actually have to use your brain. You take those loading instructions and you use them as markers. So that when you put an instruction between those 2 markers, you can now tell the length of the instruction. I say it again, do not try to understand the file format that the bytecode ends up in. It wouldn't help you, it wouldn't do you any good, it just distracts you. So here's an example where I use Kaffee and capital A's and Fefe for markers, and then since I already know what the loading instruction is, I can tell that the knob 1 is the FF in the middle. And if you're paying close attention, you will also see that the immediate values that we put there, like Fefe is not turned around. So we can tell the endians, right? Everyone knows what endianness is, right? Okay, just checking. And then you can actually automate the process. So what I did was writing preprocessor scripts, essentially, that I could feed code in, and then it would put the markers there and increase the number at the marker, and then after assembly I could take the hex dump and a very short Perl script, yes I do Perl, and have them sorted out. So what you end up with is, with this notation here, where you have the marker and the counter in the marker, and then the instruction you're interested in. Word about documentation. I've seen many people writing disassemblers and saying, well, the documentation is in the code. Or this is so cool, programming language, it's self-documenting. No, when you do this, you actually have to document manually what you find out about the instruction set, because it's the only way for you afterwards to figure out if you had a coding glitch or if you decoded an instruction incorrectly at some point. So that's the only way afterwards to verify your disassembly. And I can tell you, nothing is more disappointing than trying to understand a piece of code for many, many days and then realizing that your disassembler fucked up, especially if it's your own disassembler. Document strictly in binary is something that helped me a lot, and you're going to see why in a minute. And have examples. Like for every single instruction you write down, have an example how it looks like encoded. So the reason I'm documenting this in binary is because you then start to see patterns. So here's two instructions. One is a load into an address register 1, and one is a transfer into address register 1. And you can, since we documented it in binary, you can tell that they're only 1 bit apart, and then you can take another load instruction and see whether this bit actually, when you flip it, turns it into a transfer instruction, which happened to be the case. So it makes your documentation a lot more dense, and it makes the code that you're going to write a lot better. And then you start with the most native instructions. So for regular CPU, that would be byte operations, AND byte and another byte, or loading into all registers that you could find, and all that type of stuff. For the PLC, the most native instructions are the logic operations on inputs and outputs, also the timer and counter operations. The reason to start with the most native thing that the CPU does is because the instruction sets are very likely to be historically grown. And in fact, if you're looking at the Siemens instruction set now, I get a feeling of Intel's, because it's pretty much the same shit. They started small and then just added crap to it. And this is why you actually need to start with the most basic functionality, because you actually want to follow this timeline in order to get your stuff right and cover everything. So here's an example of an AND operation on an input 1.7, and you see the encoding there, and the NOT for that, and then you see if I do an AND operation on an input 256, I get a 4-byte code, because that's a historic development. They started to have more inputs and outputs. Many instructions take argument ranges, registers, immediates, date and time formats, what have you. And here's where the next preprocessor script comes in. You want to generate the ranges in a script and then automatically extract the bytecode, as I showed a few minutes ago, so that you're not typing by hand all the time. It's almost like writing a very dumb fuzzer. So if you ever wrote a fuzzer, it shouldn't be a problem. And then you end up with something like this. So here's a couple of inputs, a couple of outputs. Yes, the output is actually named Q, not O, for absolutely no good reason. So essentially you have the instructions, the arguments, then you combine them together in a script, and then what comes out goes into your assembler. Here's a word about notation when you write your disassembler. The notation is actually up to you. So in most cases, it makes sense to use the vendor's notation as they document their instructions, because that, you know, if someone speaks that language or that assembler already, then they can read what your disassembler produced, right? That's nice, and also you can look up stuff in the documentation. That's also nice. But there's also cases where the vendor notation simply sucks balls, and you don't want to use the vendor notation. You want to use your own. You should definitely do that, but make sure that it's clearly different from the vendor's style as well, so that someone familiar with this assembler looking at the output will immediately notice this is something different. This is what this disassembler shows differently than, you know, the vendor tools. Here's an example for where notation called change. So I said load instructions are really important because we only have one accumulator. And here's a couple of variants we have here. So you can load a counter, you can load the length of a data block, you can load an immediate value in different ways, from memory, from input, from a data block entry. A data block entry is like a struct, or most complicated with pointer dereferencing and stuff like that. And it's not clear neither from the vendor documentation nor any other material I could find whether you would consider everything after L as an argument to an L operation, or both being the actual instruction. Like, nobody says an instruction doesn't have a space in it. If you want instructions with space, fine. And then you actually have to implement what you found out, right? So you may implement your disassembler standalone, which is good, gives you complete freedom, programming language, everything. You are required to deal with everything yourself, of course, and you're lacking functionality that other tools might actually already provide, or you integrate into your reverse engineering tool. That means you're bound by whatever choice of programming languages they provided and the API. You have potential integration issues, and with IDA you will. Availability of the functionality that you already have in IDA, however, might actually help you later on. So I opted for doing the second, so I actually had to write Python. Yeah, it's Würgeschlange. So IDA actually allows you to write in Python nowadays, even CPU modules. And you essentially what you just have to do is inherit a class IDA API processor T, give it a processor ID, give it a processor ID. No, there's no automatic way to find out whether this processor ID is already taken. Define a number of basic properties about this, and then go implement a couple of functions. What you need to implement is a function called emu, and it's not the bird. This is essentially executed when IDA wants to emulate the instruction. It allows you to change things in IDB. Then there's two functions called out and out up. They're individually called back. Out actually outputs the mnemonic, and out up then the operands. You can tell it's a Russian engineering, right? No name is longer than it absolutely has to be. So ANA is then the analysis function that's called back on each individual instruction to decode a function, decode an instruction. It's relatively simple design. So if you take the small example from the IDA SDK directory, you will be actually fine. However, you should not try to deal with IDA's representation of instruction sets. So there is a large array that you have to feed where all the instructions are held, and it's highly advisable to automatically generate this. And there is, for every single decoded instruction, there is a structure called CMD that contains the effective address of the instruction and the operand. No, it's not an array, it's individual entries, op1, op2, and so on. They can have a different type, and the type actually decides what IDA's kernel is going to do with the instruction afterwards. So endianness is surprisingly a big problem with IDA. It took me more than a day to find the actually not documented global data structure called INF that has a clearly not documented field MF, which I believe in Russian means endianness. Because if you set it to 1, you're on little endian, and if you set it to 0, you're on big endian. However, if you read data, so you know the instruction decoding is called, and you need another byte or 2, the endianness is ignored. So you need your own reading function that takes care of the endianness. So I opted to essentially do 2 things, like write my disassembler completely in Python I had to, but completely independent, and have the IDA data structures create on startup, so I don't have to deal with ilfuck's wet dreams. And I can actually have classes that represent instructions and stuff. I'm only using the operand types in IDA where IDA doesn't try to be smart. So there's the IDA spec 0 to 5, which essentially means please leave it alone. And I rewrote this disassembler 2 times, should probably rewrite it again, but to paraphrase what Lisa once said about a piece of C code that I wrote for mod RM byte decoding on the Intel platform, some stuff is so ugly the code can't be beautiful. It's the same here. So if your disassembler looks like shit, but works, you're there. It's okay. So now that we can actually integrate this into IDA, have some deeper look at what we are facing with the PLC code here. So I was mentioning that there is a main organizational block that's called in every scan, right? That's the OB1, not OB1, OB1. And then there is a couple of other things. You can, in this context, you can think of a PLC like a heavily interrupt-driven machine. There's events that are real-time triggered, and then the respective code blocks are called like cyclic interrupts, or even error handling, even exceptions, or time-based calls. So OB35, for example, is a time-based organizational block that is called occasionally. Then we have functions. Functions are, as one would expect them to be, just simple code functions. They can actually take arguments, and they can actually return a value. There's function blocks. They're a bit weird. So function blocks is basically a function that has a data block, like a struct in C, assigned to it, and then gets an instance of this data block for execution. So in PLC language, the function has memory. That's how they call it. And then you have system function blocks and system functions that are provided by the system. That, you know, you can simply call them, think of them as syscalls. So the data blocks, as I said, pretty much like structs. You have instant data blocks, instance data blocks, sorry. Those are the ones that are given to the FBs, and you can, I think of them as like an object that was made out of a class. And when, oh yeah, and you have temporal data in the functions. So when you create a function, for example, you can essentially like stack variables in a C program. You can create temporary data points, and there's all kinds of weirdness with them. So Calling conventions. Calling conventions can be interesting. And here's a good case. You always have to be suspicious when you're doing the instruction set reversing. For example, when you enter call blah blah, so you're just calling an FB, which should be a very simple procedure, right? You're just calling a function. It emits all this code, everything that's red. And this is, here, if you paid attention, you will see that you're seeing the markers again, and this is why you have them, and this is why they're numbered, so you can actually tell that this is a lot of code, and it's probably actually doing more than just calling something. So it actually turns out, once I had the disassembler working, this is what happens. So, for example, here you have a call to a function block with a data block and 2 variables passed on. And this is all the code that's emitted. The most interesting thing, the actual call happens down there. The UC is an unconditional call into FB1. And this is the actual call, and everything else is parameter setup. Like, this is how it passes the arguments. Interestingly enough, when you call functions, like not function blocks, but functions, it's a completely different pattern. My guess is the functions came later, because what they do here, you know, last year I spoke about Flash and the most ridiculous things they do. Siemens actually managed to top them. So what they do here is, you see the unconditional call to SFC1, and what you see behind this, the GU, is a jump, an unconditional jump that jumps to this location right on top of the BLD +8. And in the middle, they're throwing raw pointer encoded in the instruction. There's no instruction to it, it's just argument. And they're just throwing the raw pointers in there and then jump over it so their PLC doesn't get confused about it. Ridiculous design. Addressing modes can be a real pain in the ass. Usually what happens is you think you're almost done with the disassembler and then you discover 2 more addressing modes. It happened to me, of course. So searching the internet for examples of advanced use of the programming language or environment you're looking for is very helpful. I actually finally understood the advanced addressing modes from lecture notes that a student took because he had issues understanding them. But he was pretty good documenting them. So the MC7 in step 7 actually has local indirect addressing, so you can use like a local variable and use that as a offset, so to say. So it's relative. That was the word I was looking for. And then global indirect addressing, where it actually has an address register, AR, and a pointer to it, and then you have the same as you know from the Intel platform, where you can have a register and an immediate offset. So when you put it all together, I ended up with like 463 instructions that can deal with the step 7, 300, and 400 series instruction sets. So far, everything looks good. Everything that everyone else published on Stuxnet, if it actually contained code and not political guessing. And they will have a screenshot of some PLC code. It is pleasantly similar to my results. And just to make sure that you're getting this, it's a very simple procedure, and it took the better part of 3 weeks. So there's absolutely no excuse if you need a disassembler for something and you can't get it, that you can't make it yourself. I showed you, it is not hard. And then, when you're in IDA, this is what you get, right? Finally, you can use your fun little piece of software, Russian making, to read Stuxnet code. This is the famous block C out of Stuxnet. If you see the navigation band up there, the disassembly is quite happy, and it even recognizes the functions as functions. Some of you might know the coloring. So, reading Stuxnet. Well, what's already quite known, it targets two specific CPUs. That's to distinct the target that it's looking for. It contains 3 blocks of PLC code. 2 of them are pretty identical. Some NX started to call them block A and B, so I'm staying with their terminology here so nobody gets confused. And there is a third very large block that is referred to as block C. And then in the pre-infection tests, it checks for a communication controller. That is a Profibus interface, so the usual architecture that you have with PLCs is you have controlling PLC, and then there's some industrial Ethernet or Profibus or whatever hanging off it, and there's a bunch of devices in there like variable frequency drives that run centrifuges or similar. So they're checking all this up front in order to have their Profibus communication backdoor working nicely. And then you can, of course, take tools that you have that work with IDA. Here we have a comparison between block A and B using Dynamics BinDiff, and it works nicely. Stuxnet it was pretty quickly clear that it has a fairly interesting state machine in its operation. Nowadays there's the extensive documentation that Symantec put out on what the state machine does. However, the first result that I actually had when the disassembler was just partially done was already that the widely published deadfoot magic value that you could vary over the network to find out whether a PLC is Stuxnet infected or not, will actually only return this magic value in case of state 3 or 4 within the 5 cases that it can have, which means it actually only returns this value when it's actually fucking stuff up right now. In all the other time, which is a couple of months in some cases, it wouldn't return this value. So here's a benefit of writing your own disassembler. You don't have to believe the stuff other people publish. And to get you into the mood, this is the actual function that does that. So what it does, we're just quickly covering it so you get a taste for it. So the first instruction actually goes ahead and opens a data block with a specific number. This is actually a data block. If you have that data block in your PLC, you should probably consider, looking deeper, because it's not a standard data block, it's the standard Stuxnet data block. Then it takes a value out there, which is the state variable, so it's loading a byte, loading from a data block a 16-bit value on offset 10 hex. Then it's loading a 3, the W hash 16 just means base 16. And what you see here, you have 2 loads after each other. Now I said you only have 1 accumulator register, and nobody complained. You're not paying attention. So what actually happens is once you load into the accumulator register, the former contents of the accumulator registers are shifted into a secondary, because otherwise you couldn't compare shit. Which is what happens next. It compares whether the accumulator 2 is less than the accumulator 1. This comparison alone made pretty much one day and a sleepless night headache for me, because Siemens actually managed to document the order of the operands in comparisons false. So their documentation actually says it's comparing ACU1 to ACU2, which is fine if you're looking for equal, because then it's shit equal. But if you're looking for a smaller than or greater than, then the code really didn't make sense because it never executed. So it's checking for, in this case, 3 compared to this value that it took off a data block, and then it performs a jump. RLO is the result of a logic operation. This is how they call the flag that essentially is set to 1 if shit is true. Then it'll actually, the TAC operation actually exchanges both accumulators, so you can access the one that you're not looking at right now. Then it takes a 4, makes the other comparison, and jumps, and in all other cases, returns the magic dead food and copies this also into the echo 2. In all other cases, it just zeroes out the echo registers, so even if you had code on a PLC intentionally checking for this, it wouldn't see anything. What's interesting is that there is a number of interesting hacks that you can do with an instruction called BLD. The BLD instruction actually does nothing on the device. Like, the PLC is just going to ignore it. It's like a knob, but less so. What it actually is used for is by the compiler to mark the complex calls. Remember when I showed you that a call to a function block produces this shitload of code? So when you read code back out of the PLC into your programming environment, the compiler wouldn't be able to recognize this. So what they're doing is they're having an instruction for the compiler to recognize, or for the disassembler, for their own disassembler, to recognize that, oh, here's the block that is between a BLD1 and a BLD2 instruction. This was a call to FC with parameters, and then they're turning all the code back into this simple format. So it's relatively easy for people to do tricks like this. You see, even on a PLC, you can do assembly level hacking. You just say BLD7 and then BLD8, and put some call in there, but never execute this call, but put some other code down there. This code would never be visible in Siemens tools. Now, I don't know if Symantec and other people use the Siemens tools to read the code, but it would have certainly fucked them up quite nicely. Interestingly enough, Stuxnet doesn't make use of any of those tricks. They actually kept the BLD instructions in, wasting a lot of space. So they could have just taken them out, right? And on the other hand, there's a lot more calls than BLD instructions. So part of the code was very obviously developed with the Siemens development environment, while other part of the code wasn't, or was cleaned up afterwards. Yeah, this is what you see in the Siemens tool when you do this above there. Here's part of the Stuxnet code where you see the BLDs in action. So there's two calls essentially that they made to update the process image input and output tables manually, which is pretty smart actually, because they're disconnecting the PLC from the normal scan cycle. They disable the automatic updating of the inputs and outputs and do it by hand in order to modify what the PLC thinks is on the inputs and outputs. So they're completely stealth, and the PLC is almost like virtualized by its own code. Pretty nicely done, actually. And then I was amazed to realize that, wait a minute, this code actually does have timestamps. The Siemens tools put timestamps onto every function when they compile. And I was Googling back and forth, and nobody seems to have noticed that yet. So we can actually finally say when the PLC part of the Stuxnet code was compiled. And it's consistent with all the functions. To the right you see all the functions that got compiled, and you see from its local time, wherever it was compiled, you can see this was a clean compile run. So it doesn't actually look faked. The library functions in block A and B are from 2002. The dpsend function that is backdoored was backdoored in 2006. And Stuxnet PLC code was compiled in September 2007. You know, you get this. So they're sitting on this since 2007, fuckers. What's really a nice fnord is when you look up the exact date it was compiled on, it was the day where Ahmadinejad had a famous speech at the Columbia University, stating that the Americans should actually look who was truly behind 9/11, and many people were really pissed. Maybe someone was pissed enough to compile. I couldn't do without a few notes about Stuxnet that have nothing to do with disassembler building. First thing of note here is Siemens reactions. This is an official Siemens slide from someone that is a program manager, hack-proof products. That didn't work too well, but. And essentially, what you see in yellow there is the big question whether the customer has really done all he could have done to prevent the infection. What's also interesting is it doesn't mention any patches, because apparently for Siemens it's totally okay if you're loading a data file into your programming environment and it executes code. Why would you fix that? And then a slide later, they're saying the same thing again, right? It's have a virus scanner and otherwise it's your fucking problem. Well, how about integrity checks on a PLC? I would also like to point out that I have very much respect for quality and testing that was done around the whole Stuxnet code. Everyone who did reliable exploitation in the wild for a specific target knows that, how should I say that? Essentially, you owned half the internet that is running the software you're attacking, and the target you're really targeting still refuses to give you a shell. That's the regular mode of operation in the wild exploitation. And this doesn't get easier if you pile a shitload of exploits 0 day on top of each other. So there was a tremendous amount of testing involved, and the same holds true for the PLC attack code. This is not trivial. They have insider knowledge that is not published. They're accessing data points and byte information in the PLC that is not published as what it is, but they know what it is. So that was pretty good. And what I think is, consider the fact that the PLC code was compiled in 2007, and we know about other parts that they were compiled later on up to 2009. I'm actually thinking that there has to be like a Windows GUI, which they then handed out, and then there was some, the cyber warriors that are springing up in all countries over the world. They are lightly educated, but heavily militarized, and I can totally assume that someone just went there and goes like, more is better, click, 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 more 0 days, and then fire, and that's the whole reason this thing actually escaped. I wouldn't put it past a soldier to do so. So what we should learn: developing custom disassemblers is trivial, easy, and doable. So do it. What we also learn is it takes a third-party independent researcher to even find out that Stuxnet does something interesting. So our response process as a computer security community actually plainly sucked. If this had been targeted against a Western nation's power grid, we would all be sitting in the dark and still not knowing what it actually does. I think the common estimates of O-day burn, like how much O-day do you burn on a single attack, was way too low. It was very clear that industrial control system infections were fairly easy, because that's the nature of those things. I was really surprised to learn how complex and powerful PLCs are today. So it was really underestimated how well it can be done, the infection that is. And staying with this theory that there was a nation state behind it, I would say that if you haven't started training such a team 10 years ago, you're pretty much fucked for the next 5 years. So every nation state that doesn't have like those people around Good luck. Now, this is QAF because I have a question for you. Does anyone actually have tangible information why it's called Stuxnet? I mean, here's some theories, right? But I don't know if any of those are correct. So if anyone knows why it is called Stuxnet, I would be really interested. Because I don't. Does anyone? No? Well, then I'm taking questions now.
So for questions, please line up either on that handphone or come to me.
Just an observation. Actually, it's Q for the output to avoid confusion with the letter 0 or with the 0. Simple as that.
Okay, well, ASCII, never mind. But okay. Okay. We'll see. I learned something.
I also once had a problem of writing a small disassembler for a tiny DMA engine, and I wanted to be free software, and I was looking for a generic disassembler framework where I just could concentrating on the disassembly process, and well, I couldn't find one. So my question is, A, do you know one, and B, if not, why don't you think there is such a
Oh, you mean something that not IDA? Because
Yeah,
IDA costs money. So first of all, if I read this correct, the 5.0 version of IDA just got freeware. The 4.9 definitely is. So you will need to write in C because it's not supporting Python-based CPU modules so far. But it's, you know, at least it's for free downloadable. I haven't looked at the source code of HTE. But that would come to mind as something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be horrible? Sorry. Other questions? Yeah.
Just a statement. First, I'd like to thank for your great talk in analyzing this stuff. And I can tell you, I work in this industry, and I can say, yes, there is not a lot of, I would say, engineering done. It's just, in German we say basteln. And I'm working also in try to certify devices developed according to specifications, and I can tell you, there's a lot of crap being done. It's like questions ask do people this nasty stuff? Do I really have to test these things? And it's a lot of things to discover within the next years, I assume, especially with wireless networks coming up in these areas.
Yeah, it's really interesting.
Wikipedia sagt in Notice 20, der Name ist buried or burned into the code.
Yeah, that's the problem. I didn't find it. Like, okay, it's a shitload of code, but having all the resources in the, you know, Stuxnet comes as a big DLL, having all the resources decrypted and looked at, there's not even like in different order. Yeah, they don't show up, the letters. That's why I'm asking.
Very nice talk.
Thank you. Okay, and so the annual finale party is tonight. You're all welcome. If you're there before midnight, you get in for free. And since the C-Base was too small last year, we're at the Cassiopeia Club, hier Ballerstraße. Yeah. So, thank you all for coming, and happy disassembler writing. Okay, sorry. Other questions?
Just a statement. First, I'd like to thank for your great talk in analyzing this stuff. And I can tell you, I work in this industry, and I can say, yes, there is not a lot of, I would say, engineering done. It's just, in German we say basteln. And I'm working also in try to certify devices developed according to specifications, and I can tell you there's a lot of crap being done. It's like questions ask, do people this nasty stuff? Do I really have to test these things? And it's a lot of things to discover within the next years, I assume, especially with wireless networks coming up in these areas.
Yeah, it's really interesting.
Wikipedia sagt in Notice 20, der Name ist buried or burned into the code.
Yeah, that's the problem. I didn't find it. Like, okay, it's a shitload of code, but having all the resources in the, Stuxnet comes as a big DLL, having all the resources decrypted and looked at, there's not even like in different order. They don't show up, the letters. That's why I'm asking.
Very nice talk.
Thank you. Okay, and so the annual finale party is tonight. You're all welcome. If you're there before midnight, you get in for free. And since the C-Base was too small last year, we're at the Cassiopeia Club, Ballerstraße. Yeah. So thank you all for coming, and happy disassembler writing. Horrible. Sorry. Other questions?
Just a statement. First, I'd like to thank for your great talk in analyzing this stuff. And I can tell you, I work in this industry, and I can say, yes, there is not a lot of, I would say, engineering done. It's just, in German we say basteln. And I'm working also in try to certify devices developed according to specifications, and I can tell you there's a lot of crap being done. It's like questions ask, do people this nasty stuff? Do I really have to test these things? And it's a lot of things to discover within the next years, I assume, especially with wireless networks coming up in these areas.
Yeah, it's really interesting.
Wikipedia sagt in Notice 20, der Name ist buried or burned into the code.
Yeah, that's the problem. I didn't find it. Like, okay, it's a shitload of code, but having all the resources in the, Stuxnet comes as a big DLL, having all the resources decrypted and looked at, there's not even like in different order. They don't show up, the letters. That's why I'm asking.
Very nice talk.
Thank you. Okay, and so the annual finale party is tonight. You're all welcome. If you're there before midnight, you get in for free. And since the C-Base was too small last year, we're at the Cassiopeia Club, Ballerstraße. Yeah. So thank you all for coming, and happy disassembler writing. Horrible. Sorry. Other questions?
Just a statement. First, I'd like to thank for your great talk in analyzing this stuff. And I can tell you, I work in this industry, and I can say, yes, there is not a lot of, I would say, engineering done. It's just, in German we say basteln. And I'm working also in try to certify devices developed according to specifications, and I can tell you there's a lot of crap being done. It's like questions ask do people this nasty stuff? Do I really have to test these things? And it's a lot of things to discover within the next years, I assume, especially with wireless networks coming up in these areas.
Yeah, it's really interesting.
Wikipedia sagt in Notice 20, der Name ist buried or burned into the code.
Yeah, that's the problem. I didn't find it. Like, okay, it's a shitload of code, but having all the resources in the, Stuxnet comes as a big DLL, having all the resources decrypted and looked at, there's not even like in different order. They don't show up, the letters. That's why I'm asking.
Very nice talk.
Thank you. Okay, and so the annual finale party is tonight. You're all welcome. If you're there before midnight, you get in for free. And since the C-Base was too small last year, we're at the Cassiopeia Club, Reballer Straße. Yeah! So, thank you all for coming, and happy disassembler writing. Horrible? Sorry. Other questions?
Just a statement. First, I'd like to thank for your great talk in analyzing this stuff. And I can tell you, I work in this industry, and I can say, yes, there is not a lot of, I would say, engineering done. It's just, in German we say basteln. And I'm working also in try to certify devices developed according to specifications, and I can tell you there's a lot of crap being done. It's like questions ask do people this nasty stuff? Do I really have to test these things? And it's a lot of things to discover within the next years, I assume, especially with wireless networks coming up in these areas.
Yeah, it's really interesting.
Wikipedia sagt in Notice 20, der Name ist buried or burned into the code.
Yeah, that's the problem. I didn't find it. Like, okay, it's a shitload of code, but having all the resources in the, Stuxnet comes as a big DLL, having all the resources decrypted and looked at, there's not even like in different order. They don't show up, the letters. That's why I'm asking.
Very nice talk.
Thank you. Okay, and so the annual finale party is tonight. You're all welcome. If you're there before midnight, you get in for free. And since the C-Base was too small last year, we're at the Cassiopeia Club, Reballer Straße. Yeah! So, thank you all for coming, and happy disassembler writing. As something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be horrible? As something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be horrible? As something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be horrible? As something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be home? Something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be home? Something on a Linux platform, text-based, that you could probably look into. But as I said, I've never checked the source. It might be horrible. Did I just publicly say open source could be horrible? Sorry. Other questions? Yeah.
Just a statement. First, I'd like to thank for your great talk in analyzing this stuff. And I can tell you, I work in this industry, and I can say, yes, there is not a lot of, I would say, engineering done. It's just, in German we say basteln. And I'm working also in try to certify devices developed according to specifications, and I can tell you there's a lot of crap being done. It's like questions asked do people this nasty stuff? Do I really have to test these things? And it's a lot of things to discover within the next years, I assume, especially with wireless networks coming up in these areas.
Yeah, it's really interesting.
Wikipedia sagt in Notice 20, der Name ist buried or burned into the code.
Yeah, that's the problem. I didn't find it. Like, okay, it's a shitload of code, but having all the resources in the, Stuxnet comes as a big DLL, having all the resources decrypted and looked at, there's not even like in different order. They don't show up, the letters. That's why I'm asking.
Very nice talk.
Thank you. Okay, and so the annual finale party is tonight. You're all welcome. If you're there before midnight, you get in for free. And since the C-Base was too small last year, we're at the Cassiopeia Club, here Ballerstraße. Yeah. So thank you all for coming, and happy disassembler writing.